Hello everyone, this is workshop 4, calculating moles. So remember from the last workshop we were talking about atoms, the subatomic particles that comprise them, and the different theories that were developed to get to the modern definition of an atom today. Well, when we're in the lab and we're trying to measure atoms, they are incredibly tiny. They are extremely small particles that if we were to try to actually quantify how many atoms are in some substance that we were trying to work with, it would be near impossible. And so that is where the unit of a mole comes in. 1 mole is always going to be equal to 6.022 times 10 to the 23rd. In our case, 1 mole is going to equal 6.022 times 10 to the 23rd atoms. And this number here is called Avogadro's number. For our purposes in chemistry, 1 mole is 6.022 times 10 to the 23rd atoms, but a mole is not only associated with atoms. It is just a unit to say that if you have 1 mole of something, you have Avogadro's numbers worth of something. It's the same way that if we say we have 1 dozen of something, we always have 12 of whatever item we're measuring. If you have a dozen eggs, you have 12 eggs. If you have a dozen loaves of bread, you have 12 loaves of bread. It's the same thing with a mole. Right now we're going to use it for atoms, but if you have 1 mole of anything, you are going to have Avogadro's number worth of that thing. And now the definition of what a mole is very specific as well. It comes from carbon itself, specifically carbon-12. So 1 mole is the number of atoms in exactly 12 grams of carbon-12. And it's important to know this because this will also help us also then be able to use moles to not only know how many atoms we have of something, but also how many grams we have of something. Because what this says here, since 1 mole was derived from the number of atoms in exactly 12 grams of carbon-12, this also says that if you have 12 grams of carbon, you have 1 mole of carbon. And now using this relationship here, we can say the same with other elements. The masses that are on the periodic table are the element's atomic masses, and those can be used to find the molar mass of compounds. The atomic mass of oxygen is about 16, and so if I have 16 grams of oxygen, I have 1 mole of oxygen, which also then means I have 6.022 times 10 to the 23rd atoms of oxygen. And same goes for any mass that is listed on the periodic table. And this also works if you have compounds and not just atoms themselves. And we can actually use an example to show that. So let's say we have the compound sodium oxide. In the future, you will know why this is called sodium oxide and why its name is not different, but for now we are focused on the mass. So, we just saw before that if you have an atom and you have its atomic mass from the periodic table, you have 1 mole of that. The same can still work if you have multiple atoms in 1 compound. You would just have to add all of the masses together. And so for this, we of course, as always, need our periodic table. So we need to know the atomic mass of sodium, which is 22.990. And we need to know the atomic mass of oxygen, I'll use the specific one that's on my periodic table, 15.999. So if we have 1 mole of sodium, we have 22.990 grams of it. if we have 1 mole of oxygen, we have 15.999 grams of it. And now based on the formula, the subscripts tell us how many moles of each atom we have. Sodium has a 2 next to it, so we have 2 moles of sodium. Oxygen has no subscript next to it, so we only have 1 mole of oxygen. And so to find the formula mass of this entire compound, we add together 2 moles of sodium and 1 mole of oxygen. 2 times the mass of 1 mole of sodium plus the mass of 1 mole of oxygen. And so the formula mass that we get is 61.979 grams. And so, using the same rules that we did before when we just had atoms, if I have 61.979 grams of sodium oxide, that means I have 1 mole of sodium oxide, and I have 6.022 times 10 to the 23rd atoms of sodium oxide. And so with these relationships, we can convert from grams of something into moles of something into atoms of something, and even go from grams to atoms. But always notice the relationships that we have. We know that this many grams is 1 mole, and that 1 mole is 6.022 times 10 to the 23rd. But if you're given some amount of grams, you can't directly go to atoms. I'm going to erase this up here. The pathway is always going to be grams to moles to atoms, or in the reverse direction, atoms to moles to grams. And of course, if you start with moles, you can go in either direction. But there is no way to directly know how many atoms you have from grams, and there's no way to know how many grams you have from atoms. And so that's why it's important to be able to find formula mass. You have to know the formula mass of your compound to get to your moles. If you can't get to moles, you have no way of getting to atoms. And if you're starting with atoms, you have to be able to convert those atoms using Avogadro's number into moles to get to grams. And so it should always be following, if you're starting with moles, the 1 step in either direction, but if you're starting with grams or atoms, it should always be a 2-step process. You should never be going directly from grams to atoms. So let's look at these first set of practice problems that are here on the worksheet. So for 1 and 2, they want us to just calculate formula mass of a compound. And the first compound they're giving us is aluminum oxide. So just like before, we care about the elements that are present and the number of elements themselves. So we get the number from our subscripts. And so we have aluminum and we have oxygen. Aluminum has a mass of 26.9815. And oxygen, as we saw before, has a mass of 15.999. For sake of calculation, I'm just going to round that to 16. If you want a more exact answer, you can leave it as 15.999, but your answer should still be within reason by the final result. It should only be off by a few decimal places, whether you use 15.999 or 16. And so it's okay if we round it early. So we have 2 moles of aluminum, so we're going to 2 times 26.9815. We're going to add that to the 3 moles of oxygen we have times 16. So 2 moles of aluminum, 3 moles of oxygen. I'm actually going to change this real quick. Since we're using the periodic table amounts, we're going to use the units AMU. In terms of numerical value, your answer is not going to change. Grams and AMU numerically are the same value, just that AMU is going to be your atomic mass units, while grams are used when actually measuring out samples. So 2 times 26.915 plus 3 times 16, and we should get 101.96 AMU. And so the formula mass of aluminum oxide is 101.96 AMU. And also, since AMU and grams are interchangeable numerically, you can still use that in your calculations and conversions. Even if even if on the periodic table they are atomic mass units, when you're converting from moles to grams, you would still put it in grams, not AMU. So now we have calcium phosphate. Notice that, get the red marker. Notice that phosphate itself, PO4, is a unit on its own, and it's in parentheses with a subscript 2 on the outside. That's going to be very important when doing our calculations, because even though phosphate itself is a single molecule, we are still going to add up each individual atom to get our formula mass. So we have calcium, which has a mass of 40.08, sorry. We have phosphorus, and we have oxygen. When you see a 2 on the outside of parentheses, or any subscript, if you see any number on the outside of parentheses, we're going to treat that like multiplication, because what this is saying is that you have 2 moles of phosphate. If the 3 here is telling us we have 3 moles of calcium, the 2 being on the outside tells us that we have 2 moles of phosphate itself. And if we have 2 moles of phosphate itself, then we have to double everything that is in the parentheses. So we actually have, well, actually, let's rate the masses first. For phosphorus, we have a mass of 30.9737 AMU. Oxygen is again going to be 16 AMU. And so now when we set up our calculations, it's 3 times the 40.08. I'm actually going to move this up so I have more space. So I'll just box the answer at the end. So 3 times 40.08. So we have 3 moles of calcium atoms. And now when we look at phosphorus, we're not going to put 1. This 2 on the outside tells us that we have 2 moles of phosphorus. So it's 2 times 30.9737. And the last part, we already have 4 oxygens in phosphate, and we now have to multiply all of those by 2. So we're going to have 8 moles of oxygen. So 8 times 16. A subscript on a lone atom tells us you have 3 moles of that atom, and so a subscript outside the parentheses says you have 2 moles of whatever is inside the parentheses. And so you have to multiply any numbers within those parentheses to get the correct amount of atoms, or moles of atoms that are in said parentheses. And so when all this gets added together, you get a mass of 310.18 AMU. I also notice I'm gonna tend to drop my units as I'm doing calculations like this. It makes it easier to read and it's a little bit faster so long as you remember to put your units in your final answer. Your final answer does have to have units, but your calculations themselves do not. So 1 and 2 are formula mass. Now the rest of these questions have us doing some type of conversion. So for 3, calculate the number of, oh, I wrote the wrong thing, sorry. Calculate the number of argon atoms in a 1.745 mole sample of argon. So we are starting with moles of argon and we want to get to atoms. That is going to then utilize Avogadro's number. You're going to notice that a lot of these calculations are dimensional analysis, is taking our knowledge of these units, 1 mole is equal to Avogadro's number, and setting it up as a fraction to be able to get out of moles and into our desired unit, in this case, atoms. So if 1 mole, I'll write it with our arrows, if 1 mole is equal to 6.022 times 10 to the 23rd, then we can say that in fraction form, 1 mole per every 6.022 times 10 to the 23rd atoms. And of course, we can flip that. 6.022 times 10 to the 23rd atoms per 1 mole. It's whatever orientation we need it to get out of the current units and get into our desired units. We are starting in moles. We want to get to atoms. If moles is in our numerator, that means we need moles in our denominator in our conversion factor. And so if that's the case, that means we need Avogadro's number in our numerator. When going from moles to atoms, Avogadro's number is in your numerator. And like we said before, moles is just a unit. You can have a mole of anything, and so we're going to label this as argon atoms for every 1 mole of argon. So now our units can cancel out like that. So 1.745 times 6.022 times 10 to the 23rd. When we have this many moles of argon, we have 1.051 times 10 to the 24th argon atoms. And now for 4, we need to go in the opposite direction. We have 1.97 times 10 to the 25th phosphorus atoms, and they want us to convert to moles of phosphorus. How many moles of phosphorus atoms does the sample contain? So we're going to do the same math, but once again, we're trying to get rid of these units here. Atoms is currently in our numerator, so that means in our conversion factor, we need atoms in our denominator. So it's now 1 mole per Avogadro's number. Of phosphorus atoms. And now again, phosphorus atoms cancels out with phosphorus atoms. When you are doing these calculations in your calculator, I should have brought this up in the last one, but I can bring it up now. Make sure anything with scientific notation is in parentheses. Your calculator is not going to understand that this is a number by itself, and so in this calculation, it wouldn't have any major effect because it's multiplication. So we're going to read it left to right, it's fine. But the calculator would do 1.745 times 6.022 and then multiply that by 10 to the 23rd. But when you're doing division, it is extremely important to have both of these in parentheses. Because if you don't have it in parentheses, it's going to do 1.97 times 10 to the 25th divided by 6.22. Without the parentheses though, it sees as multiplication symbol, so it will divide this by 6.022 and then multiply that entire number by 10 to the 23rd. And that would not be correct. So when we have 1.97 times 10 to the 25th phosphorus atoms, we have 32.7 moles of phosphorus. And now last one, for question 5, calculate the mass of zinc in a sample containing 0.892 moles of zinc atoms. Now they're saying moles and atoms at the same time, so you might think you have to use Avogadro's number in this case, but they're telling us that we have 0.892 moles of zinc. They're not telling us that we have atoms necessarily. It's just the wording of the problem is a little bit more tricky. But ultimately, we are starting in moles, and we need to get to grams. So just like here, we have two ways of setting up our conversion factor. MM is going to stand for molar mass, or FM, which is going to be formula mass. And so, just over there, we can either set it up as 1 mole per whatever your molar mass is, or you can flip the other way around. Molar mass per 1 mole. In this case, we are starting with moles, and so if moles is in our numerator, we need moles in our denominator, so the molar mass of zinc is going to go in our numerator then. 1 mole of zinc on the bottom, and these will cancel out. And so now, to get from moles to grams, we know that 1 mole of something is equal to its molar mass, or formula mass, in this case, molar mass, it's just an atom. And so if 1 mole of zinc is equal to its molar mass, we use the periodic table to find its mass. And so zinc has a mass of 65.4. As I somewhat mentioned before, if you are rounding your molar masses differently, that is completely fine. Your answer should still just be within reason. Off by maybe some decimal places, at worst off by the ones place, but for calculations like this, it's usually just off by some decimals. So, moles times the formula mass, or molar mass, sorry. Moles times molar mass to get grams. When we have 0.892 moles of zinc, we have 58.3 grams of zinc. And so those are the first 5 questions. And now we are on to 6 through 10, which are going to involve a few more steps. Question 6 starts with our first instance of having to use the entire pathway when doing our calculations. How many mercury atoms does a 0.966 gram, oh, that's not the symbol for mercury, Hg. How many mercury atoms does a 0.966 gram sample of mercury contain? We are starting in grams, and we want to get all the way to atoms. Remember, we know that the formula mass or molar mass of a substance gives you 1 mole of that substance, and 1 mole of a substance is Avogadro's number's worth of atoms, but we can't say exactly how many atoms this 0.966 gram sample of mercury is directly. We have to go first to moles to get to atoms. And so if we're going to moles first, we have to know the molar mass of mercury. So that first step, getting out of grams and into moles. Grams is in our numerator. We need our molar mass then in our denominator. So for every 1 mole of mercury, you have 200.59 grams of mercury. And that is our first step. So, grams in our numerator, we put grams in our denominator in our conversion factor. That leaves us moles in our numerator. We want to get to atoms now, so we need a conversion factor that gets rid of moles. If moles is currently in our numerator, we need moles in our denominator. And so now if we have 1 mole of mercury, or we don't have 1 mole, but if we have converted this sample of mercury into moles of mercury, we now put 1 mole of mercury in our denominator. These cancel out. Oh, that's way too big. Need space. There we go. And 1 mole is equal to Avogadro's number, and that is how many atoms of mercury we will have in this sample. So first, dividing by molar mass to get into moles, and then multiplying by Avogadro's number to get into atoms. So do these calculations separately in your calculator. Do the mass divided by mass first, and then the number that you get from here, multiply by Avogadro's number, and of course, always remember your parentheses. And when the calculations are done, we find that 0.966 grams of mercury is equal to 2.90 times 10 to the 21st mercury atoms. And this is what I meant when I said earlier that it should always be a two-step calculation if you're starting with grams and going to atoms, or starting with atoms and going to grams. For number 7 and for number 8, we are taking a step back a bit. What is the mass in grams of 2.37 mole sample of lead oxide? So we are starting with moles, and we just want to get to grams. This is a one-step conversion. 2.37 moles of lead oxide. But now, before we were working with lone atoms, we were using molar mass. Now this is a compound, and so we have to use formula mass. We have to find the mass of lead and the mass of oxygen. And so we have 1 mole of lead. It doesn't have any subscript next to it, and we have 2 moles of oxygen. And so when we add up the masses, lead is somewhere in here. Here it is. The molar mass of lead is 207 grams. And we're going to add that to 2 times our 16. And when you add these two values up, lead oxide has a molar mass of 239 grams. And so now that we know the molar mass, we can take our moles and convert them into grams. We are starting with moles, which means moles is currently in the numerator of this problem. And so for our conversion factor, we need moles in the denominator. There's 239 grams of lead oxide per 1 mole of lead oxide. These two cancel out, we'll be left with grams. And when we have 2.37 moles of lead oxide, we have 566 grams of it. 566 grams of lead oxide. Similar for number 8, but now we're going in reverse. How many moles are present in a 15.92 gram sample of calcium chloride? 15.92 grams of calcium, that's not the formula, CaCl2. So once again, we have to pay attention to our subscripts to know how many of each atom is in this compound, so we can then add up our molar masses. Calcium has a mass of 40.08, and we only have 1 mole of it, so 40.08 grams. We have 2 moles of calcium, and the mass of chlorine, and the mass of chlorine is 35.45 grams. And so the molar mass of our calcium chloride is 110.98 grams. So now we have the formula mass to be able to convert from grams to moles. So 15.92 grams of calcium chloride. Grams is currently in our numerator. We want grams then in our denominator, so the units cancel out. And so that means, to set this up correctly, we have 1 mole of calcium chloride per every 110.98 grams of calcium chloride. Grams has to go on the bottom for our units to cancel out and get into moles. So if you have 15.92 grams of calcium chloride, that means you have 0.1434 moles of calcium chloride. Right, and now for 9 and 10, we're going back to a setup similar to 6. We're using our full pathway of grams to moles atoms, or atoms to moles to grams. So for number 9, how many carbon atoms are present in a 1.75 gram sample of HC2H3O2? That is a type of acid, and I cannot remember the name of it at the moment, but you will not be expected to know the name of it either, so it's not too bad. C2H3O2. And now notice the wording in the beginning of the problem. How many carbon atoms? They're not asking for atoms of our acid over here. They're asking just for the amount of carbon atoms that there are in the actual compound itself. But we're still going to do the same steps. There's going to be an additional step done at the end. So we're starting with 1.75 grams. Same work still applies. We have to find the formula mass if we want to get from grams to moles, to then get from moles to atoms. So, marker. 2 moles of carbon, 2 moles of oxygen, and make sure you add up all of your hydrogens. We have 3 here. We also have 1 here. These are going to add up to 4 moles. And so for the mass, we have 2 times 12.01 plus 4 times 1.01 plus 2 times 16. And so the formula mass of HC2H3O2 is 60.06 grams. And so now we can do the first step of our conversion. Will I have enough space? I don't think I will. So I'm going to actually just make it a little bit small, but we'll fit it over here. We're starting with 1.75 grams of it. Grams is currently in our numerator, and so we need grams in our denominator in our conversion factor. So 1 mole goes on top. And 60.06 is going to go on the bottom. So we've gone from grams to moles. We want to get to atoms, and so now we have to convert from from moles to atoms. Actually, I was going to do this in a different order, but let's not do atoms yet, because remember, we are focusing on carbon, not the entire compound. Just like how we use these subscripts to tell us how many moles we have to find our formula mass, we did 2 times 12.01 to get the mass of all of the carbon that is in this compound. You can do the same thing to convert between each individual atom in this compound. If we have HC2H3O2, that means for every 1 mole of this compound, we have 4 moles of hydrogen. For every 1 mole of this compound, we have 2 moles of carbon. And for every 1 mole of this compound, we have 2 moles of oxygen. And so in our conversion factor, we're going to have moles both on the top and bottom, but that's why writing out the full compound is important to keep track of what you are converting out of. If moles of HC2H3O2 is on top, we're going to put 1 mole of HC2H3O2 on the bottom, and based on the formula, there's 2 moles of carbon in this compound. You need 2 moles of carbon to make the compound. If you don't have 2 moles, you know you're not able to do this work. And so now that we are in the moles of the atom that we are specifically focusing on, we can find out how many carbon atoms there specifically are in this compound. And this is the same work as before. We have moles in our numerator, we need moles in our denominator for this to cancel, and so we're going to multiply by Avogadro's number. Carbon atoms for every 1 mole of carbon. That's still true. If we have a mole of carbon, we have Avogadro's number's worth of carbon atoms. And so when we have 1.75 grams of HC2H3O2, we have 3.51 times 10 to the 22nd carbon atoms. And now I did the multiplication here just to make sense of where the 2 is coming from, showing that you convert from moles of the original compound to moles of carbon specifically in said compound. But you saw that I was going to do the math a little differently. I was going to multiply by 2 at the end. And that is also acceptable, because if you multiply by 2 at the end, you're still saying the same thing. Because you would get 1 mole of our original compound, multiplied by Avogadro's number. That would be atoms of the compound, but there's 2 moles of carbon within said compound, so you still have to multiply by 2. So whatever step of the way you want to do it is fine, so long as if they're asking for a specific atom in the compound, you multiply by whatever subscript you see next to it. So if in this case, if they were asking for a number of hydrogen atoms, you would multiply by 4 here instead of 2. And if it's a case like calcium chloride, if they were asking about how many calcium atoms were in this compound, you wouldn't multiply by anything. It's a subscript of 1 because there's no subscript there. And so the moles of the atoms of compound is equal to the atoms of specifically calcium. And so now for the last one, now we have a sample, it's the same sample. So it's HC2H3O2 again, but now we have 4.82 times 10 to the 26th oxygen atoms. And we want to know the mass of the entire compound, the HC2H3O2, in kilograms. A lot of the work's already done from question 9. I don't have to calculate formula mass. We're just going to use the same value because it is the same compound that we're working with. But now notice we're starting with atoms of specifically oxygen, while here we ended with atoms of specifically carbon. It's going to follow the exact same order of steps, but we're just going to go in reverse. So we're starting in atoms, which means it's in our numerator. We want to get to moles, and so we're going to divide by Avogadro's number. Every 1 mole of oxygen is made of 6.022 times 10 to the 23rd oxygen atoms. And now we are going to focus on the fact that we are working with oxygen specifically, but we want to get to our original compound, HC2H3O2. There's 2 moles of oxygen in this compound, and we're trying to get out of moles of oxygen. So before we multiplied by 2 because we were trying to get to carbon, now we have to divide by 2 because we're trying to get out of oxygen. So there's 2 moles of oxygen for every 1 mole of our compound. You cannot make this compound without 2 moles of oxygen. And so now moles cancel out only for the oxygen. We're still left with moles of our acid. And so now the last part is that we want, well, almost the last part, we need to get to kilograms. Kilo is just a prefix. The main thing to focus on is grams. And so we still have to get to grams of our acid here. If we are currently in moles, we would have to put moles in our denominator to cancel them out. And so now we're going to multiply by 60.06 grams. every 1 mole of HC2H3O2. And I'm actually going to put the answer here before I convert it into kilograms just to show the work. I actually don't have that right now, so give me a second. By 2, multiply by 60.06. So if we were just in grams, we would have 24,043. Did I put decimals in mine? I did not. Which makes sense because we have to divide it anyway. Grams of our sample. Like I said, the work is the same, just in reverse. We start with grams here, we divide by mass, multiply by the amount of carbon, multiply by Avogadros. We start with atoms here, we divide by Avogadros, divide by the amount of oxygen, multiply by the mass. Same order of steps, just all reversed because we're going in opposite directions. And that's going to be true for any of these problems. The steps are going to look very similar. Here it's going to flip your fractions depending on which direction you're going. And so now the last part is just to get this out of grams and into kilograms. I'm going to use the textbook's notation for this. So grams is in our numerator. We want grams then in our denominator when doing this work. So for every 1 kilogram, there is 10 to the third, or 1,000 grams. And so we move the decimal over 3. We have 24 kilograms of HC2H3O2. If you're dealing with just a specific atom in a compound, it only adds one additional step, multiplying or dividing by the number of moles of that atom that are in the compound, because you need that amount to actually create said compound. If I don't have 2 moles of carbon, I can't make our acid. If I don't have 2 moles of oxygen, I can't make our acid. That is the end of this workshop. If there are still any questions on the content that was covered in this recording, absolutely reach out to the Math and Science Resource Center here at John Jay to get more assistance. You can book an appointment yourself through John Jay Navigate, or you can go to the Tutoring Center on campus, room 1.94 in the new building, and someone at the front desk can help you book an appointment. You can book one-on-ones either in person or virtually, and there are plenty of tutors here who can help you understand the content better.